family. A big fan of my own, she said. I don't need you inside my head. She big fan of me. She big fan of me. A big fan of my own, she said. All my love's like a shade to red. She big fan of me. She big fan of me.
Hello, how's it going? Just dancing a little bit. Welcome to Bed Talks, TED Talks in my bedroom for Calc 3. I hope you guys are all doing well. So it's going to be something I'm going to do, hopefully a little bit more, post some just concepts, problems that you guys have gone through and problems that you guys want me to go over, some concepts that maybe you've forgotten about or want some more discussion on. So you guys a little bit more of a chance to kind of dictate where we're going to go forward. So today I want to talk about limits in two dimensions, at least to kind of remind ourselves going forward how we need to do that. I'll go over a problem too, and I'll go over some concepts and how we get to that idea. So as a reminder of what the idea of a limit is, let's talk what we know in one dimension, right? How do we know in one dimension? So let's assume I have a function, f of x. Here. There's a function, a one variable function here. And I want to find out the limit of a function. Let's say the limit here. Now, is this limit defined even? Right, what is the concept of a limit in one dimension? Well, Calc 1, we kind of saw that this limit is defined if a couple things hold, right? Well, it doesn't even have to be defined as a function there. If it's defined going from the left and from the right, going to the same point. So if I go from the left here and go up, and if I go from the right, this function traverses from the left and right, it approaches the same exact function height. If that's true, then we can say this limit exists. And the limit exists, so let's say this point's a. We know that f of a, in this case, is where our limit is. So we can kind of say that we need the limit as x approaches a from the left of f of x is equal to the limit as x approaches a from the right of f of x. If this holds, then we know that the limit actually exists, and we can find the limit value. Now, just as a reminder, we're allowed to have limits here. Let's say this isn't even defined. This limit still exists because we have the going from the left and from the right. We remember that the function value does not have to exist for a limit to exist. If it's continuous, or if a function is continuous, we need both these conditions to hold. We need the limit from the left and right to happen, to be consistent, and we also need the function to be evaluated at that point. Now, when do we know that a function limit doesn't exist? Well, if these things don't hold, right? Maybe something like, I have something up there and coming back like that, right? The limit coming from the left and the limit coming from the right are two different parts, right? If I come from this point, I'm up here, this one down here. So we see that this limit does not exist. So the overarching theme and the idea here in one dimension is that if I come from the left, I come from the right, they have to be approaching the same point. If they do, the limit exists. If they don't, the limit doesn't exist. How do we do this in two dimensions? Or how do we extend this to two dimensions? It's not obvious kind of how to do that. Well, let's kind of think about it this way. Take this function, for instance. xy over x squared plus y squared. Now, I hope you'd agree here, this is the function x squared plus y squared, like that. I hope you'd agree that the point 0, 0 is not defined, right? F of 0, 0 is not defined, is not defined, right? Because it's a 0 in the denominator, 0 over 0. So how do we show that this limit, if this limit exists, limit doesn't exist? Because we know, as we saw in the previous one, this limit could exist though. Now let's think about this though. In the last time, we had a one-dimensional sense of our x, right? We only could go from the left, we could approach from the right. But now, think about what's happening here. Imagine you're on a mountain and you're attempting to get to the top of the mountain, right here. There's many different ways you could technically get to the top of the mountain, right? You come from this direction, you get to this direction, you come to this direction, maybe in this way, maybe in this way, maybe like that. Maybe if you're on, like I use an e-scooter going here, right? There's so many different ways I can get to that top of the mountain, or maybe just, a different point. And there's so many different ways I can get there. Let's assume that I'm in an open world. I have to make sure for a limit to be defined in this sense, I need all of these different trajectories going to my point 0, 0 to be the same, to go to the same function value. If any one of them goes to a different function value, then the limit does not exist. Imagine that you're at the Grand Canyon Right, imagine you're at the Grand Canyon, and one of you starts from the top of the canyon, one of you starts at the bottom of the canyon. If you're right over each other, which you can be at some points, right? You've come from a very different direction. Maybe you come from the west, maybe I come from the east. One of you's all the way at the bottom, one of you's all the way at the top. It's a completely different function value. And so therefore you're going from two different points, but you're getting to the different one. And that's therefore the limit does not exist. There's a huge discontinuity there because, you know, the Grand Canyon. So what we need to do is to show this limit exists. If we were to show this limit exists, so we need to show that all of these, every single trajectory going to my point 0, 0, goes to the same exact function value. Now, if you can imagine, how many different directions are there? There's infinitely many. So it would take a very long time to prove that all of them work. Now, to show that something does work, a limit does work, it takes a lot of hard analysis. It takes a lot of very, very big and technical stuff to do, like delta epsilon proofs. You might have seen that in the past. But what we're going to be mainly deciding about, we're going to show some tricks to show where some of them do exist, but overarchingly, we're going to be showing why limits don't exist. And the way to show that a limit doesn't exist is we need to find two curves, maybe a curve C1, maybe a curve C2, such that the limit, maybe this limit is L1 and this limit is L2. If the limit going to this point is maybe L1 for this one and L2 for here, I have found that there's this huge discontinuity, right? I'm coming from this direction, you're coming from this direction, and they're ending up at this different heights, which is going to show a discontinuity. My goal then is to show that I have two different limits. I need to find two curves, two trajectories to my point, such that the limits are different. I need to find that L1 is not equal to L2, where C1 and C2 are different. If I'm able to do that, I win. So let's kind of think about that. So let's tackle this question. It's a more general sense. And basically the question I'm asking, more formally, is to ask the question, you know, does the limit of xy going to 0, 0 equals what? The limit as xy approaches 0, 0. Does that exist? This is how we kind of write it. The points xy going to 0, 0. Now, it's always going to be helpful for you when you ever do this type of problem to just draw out your ideas. And now the goal is, especially to this one, you want to start to come up with a couple easy trajectories to kind of think about, you know, where am I going? What are some easy trajectories for me to go at? Is there anything I can gain some insight on? So here, the easiest trajectory, we're going to this point. So the easiest trajectory you kind of imagine are, I'm going in the x direction, maybe the x-axis and the y-axis. Probably some easy trajectories there. A little bit easier because they're very horizontal. Now, the big thing that we're going to want to do when we pick a trajectory, we're going to want to change this. This is a multi-dimensional limit. I'm going from x and y to 0, 0, which is kind of tough. But what I'm going to be able to do by these trajectories is change this into a one-dimensional limit. That's what's going to be really important. So take the x-axis. What do I know about the x-axis? On the x-axis, y is 0. Right? Y is 0. So what I'm going to do then is I can replace y equals 0 everywhere in this limit. Kind of cool. So what I could say is the limit as xy goes to 0, 0 of xy over x squared plus y squared is equal to, well, I'm going to plug in 0 for y. So this is now just x going to 0. Now it's just worrying about x going to 0, and I know what y is. Y is 0. Over x squared plus 0 squared. As you can see here, x times 0 is 0. So this whole thing's 0. So that means on this entire line, actually on the x-axis, this function is 0. So therefore going to that is going to be 0. Okay. Let's try the y-axis. Now we note, if I get another number other than 0, then I'm already done, right? I've shown that I have two different trajectories that have different function values. In this case, on the y-axis, I have that this means that this is x equal to 0. How about doing this now? The limit as xy going to 0, 0 of xy over x squared plus y squared. You can probably see what's going to happen again. Because now I'm plugging in x equal to 0. If I'm plugging x equal to 0, this whole thing is going to become 0 again. In the same exact vein here. And so therefore, this is also going to be 0. So we've shown that we have on the y-axis and the x-axis going to this point on this curve. We see that we enter and we're going to hit 0, 0 at the function value 0. So we have two curves, they have the same limit. So we see that the limit can still exist. Now we only have an infinitely many more directions to go. Uh-oh. So I guess here, what do we do next? What's the next obvious choice? The next choice you could probably imagine would be maybe, probably the easiest one would be the line. Right? What line goes through y equals, well, 0, 0? Maybe y equals x. Right? There's a line like this. Maybe y equals x like that. So let's try y equals x. Let's try the line y equals x. Now, what do I know about these coordinates? Right? These coordinates look like x comma x. I hope you'd agree on that. They all look like 1, 1, 2, 2, 3, 3, a million, smiley face, smiley face. That goes on like that. So here what I'm going to do, same idea. I'm going to now replace every single place I see y, I'm going to replace it with x. Going to 0, 0 of xy over x squared plus y squared. Well, here, it's now x going to 0. I'm going to replace x with y with x. X times x divided by x squared plus x squared. Just replacing the x's with the y's. We now get here, as you can see, this becomes x squared. Down here we can combine these to make 2x squared. Huh, that's kind of cool. X squareds cancel, I'm left with 1/2, and therefore the limit as x goes to 0 of 1/2 is 1/2. So what is this saying? This says if I travel on the line y equals x, I'm going to be going to 0, 0, and at this point it's going to approach the function value of 1/2. I'm going to reach it from a height of 1/2. If I approach it on the x or y axis, I'm going to approach it at a height of 0. It's kind of like a Grand Canyon again, right? As you can see, I have two different trajectories that are going to get me to different points. And so therefore, because I have a 1/2 here and a 0 here, I have two different trajectories to my point that give me two different function values. Therefore, the limit does not exist. That's kind of the idea. Now, in this vein, you might see a pattern. Like you might say to yourself, well, Nick, that's all good and well, but how did you guess that y equals x would have been the case? What if it's a really complicated thing, maybe of something like this? Good question. You kind of see something that kind of worked its way pretty well here. If you notice, for x equals 0 and y equals 0, we always got 0 on the top. So zeros are not going to really work out very well. Now, what happened here? We got the degree on the top and bottom, the highest exponent on the top and bottom to be the same. So, because they canceled out then, right? So if we're able to do that, that might be a good thing to do, right? Plug in something that would give me give me the same power on the top and bottom. So for instance, let me give you some example of that. What if I did something like, I'm using this as my eraser, don't know why, it's the only thing I have. What if I gave you something like this? You say to yourself, okay, well, where do I go now for this guy? It's a little bit tougher. I hope you'd agree that still, in this case, 0, 0 is undefined, right? X, y to the 4th, x squared plus y to the 8th. I hope you realize that 0, 0 is not defined. And if I go on the x or y axis, I'm going to get 0 again because these things are 0 up here. So now, how do I do this? Well, I note that the highest degree on the bottom is 8, right? I have y to the 8th. And if I want to get a y to the 8th on the top, maybe. If I get a y to the 8th on the top, I would probably want x, or if I let x to be y to the 4th, I would maybe get a y to the 8th. This guy would become a y to the 4th squared, or y to the 8th. So if I just take this, if I take the trajectory x equals y to the 4th, which is some parabola, like parabolic thing like that, going in that direction. If I did this, right, what would happen then? This equation would then become y to the 4th, y to the 4th, over y to the 4th squared plus y to the 8th. And if you know here, this becomes y to the 8th over 2y to the 8th, which is 1/2. And so therefore we can again rule out that this function is defined because of that fact. So a cute little trick there. The big trick to note, especially if you have something like this, is to realize that if I'm trying to show that something's limit's not defined, try to get the degrees on the top and bottom together. Usually, degrees on the top and bottom the same. It usually helps out immensely. So again, the concept again here, for a limit to hold in 2 dimensions, we need to check every single direction to make sure they all go to the same exact height, like a mountain peak. Right? They all go to that same point. We don't want, if we have something like the Grand Canyon where we have 2 different directions coming together and we have 2 different function heights, that's going to be kind of an issue. That's why the limit does not exist there. And this is a nice little technique. So yeah, that's this idea for limits here. If you have any questions, let me know, and I'd be happy to think about what I can help on this type of problem. I'm going to posting on partial derivatives coming up next, so let me know if you have any other questions. And hippocampus, can you take me out?
Growing pains, playing rain on the high sea. Scale a tree, step a branch so you can't leave.
Hope you guys are doing well. Stay safe. And yeah, I'll talk to you later on Bed Talks. Bye.